Today we will do the experiment 8. And this experiment, with this experiment, we will generate a schematic from the Verilog code. Generating schematic from Verilog code is called RTL synthesis. RTL can be is the programming language for the circuit description. It can be either Verilog or VHDL. And synthesis means generating something indirectly. Usually, we draw the schematic, then we can do the simulation. But in this experiment, we will write the Verilog code first, then we will generate the schematic from the Verilog code. And we will see how we can do that. And the tool that we are going to use is called CadenceGenus. So this is what we are going to do today, RTL synthesis of a digital subsystem using CadenceGenus. The first thing that we need to do is to log into our Cadence server. Xming is running. Then we will run party. Select VLSI lab and open. Then you can write your user ID. Then write Nautilus. So it will let us to log into our server. Now the next step is that we will go to our home directory, then your VLSI underscore your student ID. You can go in there, and then we can open in terminal. Now we have to create a new folder, and the command to create new folder is mk make dir, make directory, mkdir. There is a typing mistake here. You can see it's a experiment 7, but we will name it as experiment 8, exp 8. Okay. Now we can go inside this new folder. In order to do that, we have to write cd exp 8. Then we have to create few more folders. Make directory. One will be RTL. Another make directory will be called synthesis. Then third directory mkdir. One more directory. And the last one is Right. So these are the list of the folders that we have to create. Now, as we have done in the previous experiment, we will have to write a Verilog code so that we can use it to generate our schematic. The main objective for this experiment is to generate the schematic. So we will not focus on the Verilog code. What we will do, we will use the code here that is given here. We'll just copy it and paste it in our Cadence server. Okay. Now, the step to now copy and paste the Verilog file you used in experiment 6 for counter in the RTL directory. So let's go to the RTL directory. So you should be able to see the experiment 8 folder. Then we have RTL directory. And we can create a new file. Press right button. Create document, empty file. And we can name it as upcounter. .v. Let's open this file. Now we can paste the code for the up counter. Just to go through this code, module, up counter, we have three inputs, three signals. One is input is reset, another input is clock, and output is Q. As you can see, inputs are reset and clock, output is Q. However, this output is actually 4-bit, so we are generating a 4-bit up counter. So in order to define more than 1 bit, this is the syntax to define more than 1 bit. So in this case, we have 4 bits. How is it 4 bits? If we start from 0, 0, 1, 2, 3, so that will give us 4 bits. Now, always for the positive edge of the clock and also the positive edge of the reset, if the reset is high, then Q will be Q will be 0. Otherwise, Q will be Q plus 1. So for every clock pulse, Q will be increased by 1. So that's a simple code, end and end module. All right, so we are done with the second step. Let me close it. Now we have to copy two files. One is the fast.lib, another one is slow.lib. So in order to, these two files are saved somewhere else in this server. So we have to copy these two files from that location to your working directory. All right. In order to do that, we have to go inside experiment 8. As you can see, this is a typing mistake. It should be experiment 8. So let's do that. Okay. As you can see, we are already in experiment 8. So what we need to do, we need to go to library folder inside experiment 8. There. Now we can copy these two files, slow.lib and fast.lib, in our library folder. The copy command is cp space /home /brag, and the file name is slow.lib, and we have to place a dot at the end. If I press enter, this file will be copied.
Sir, dot টা কি স্যার স্পেস দিয়ে দিব স্যার?
Yeah, there will be a space up before the dot. So slow.lib space dot. Okay, now we can copy the other file fast.lib ast and similar syntax. Press enter. The fast.lib and the slow.lib will be copied to the library folder. And now the next step is to copy another file, that is rc_script.tlc into synthesis folder. So we have to go to synthesis folder. Now we have to get out of library folder. In order to do that, we have to do cd space .com. As you can see, we were in the library folder. Now we are in the experiment 8 folder. We have another folder called synthesis in the experiment 8 folder. So I will do cd synthesis. Right. So now we are inside synthesis folder. We have to copy the file rc_script.tlc tcl. The same command cp space /home brag then rc_script.tcl space dot and press enter. This file is also copied in the synthesis folder. Next step, we have to copy another file called constraint. Right, and we have to copy this constraint file inside the constraint folder. So let's get out of this synthesis folder first. Let's go into constraint folder. Now we can copy the constraint file. And space dot. So step number 5 is done. Now what we have to modify some of the file, and let's see how we can do it. So now let's step number 6. Now go to the synthesis folder and open tcl file. Change the file names accordingly in lines 4, 8, and 9. In lines 1, 2, and 6, specify the location of the library, Verilog file, and constant file respectively. So let's take a look at this file. So we have this file rc_script.tcl. We can open it. So first we have to modify line number 4, 8, and 9. So what do we have for line 4, 8, and 9? This is line number 1, 2, 3, and 4. So here you can see there is a file name called counter.v, but the file name that we used is up counter. So we have to modify this file name to up counter. So that's the first change. Now line number, this is 4. We have to go to line number 8. This is 4, 5, 6, 7, and 8. All right. So we can see the at the end of this simulation, the simulation output will be written in counter_netlist.v, and So because we are using up counter, we can name it as up counter underscore netlist dot. Another file that the simulator we use, we are not going to discuss it, but just so that you know, there is another output file called SDC file. So this output file is required for the next level of simulation. Because we are using up counter, we will change the name to up counter also. So these are the changes that we will need to do initially. Then next step is in line 1 to 6, specify the location of the library and Verilog file and constant file respectively. So 1, 2, and 6. Let's take a look at 1 to 6. So 1, this is the line number 1. The library file, all the libraries, remember we just copied 2 library files, slow and fast. Those 2 files are in this lib folder. And also the Verilog code that we have written or copied actually in this case are saved in RTL folder. So those 2 folders, the name of those 2 folders are correct here. So we don't have to change it. Now we have to go to line number 6. What do we have for line number 6? 1, 2, 3, 4, 5, and 6. Okay. So here if you recall, we created a folder called constraints. Now we have to be very careful with the names. Okay. So let's take a look at what is the name of this folder exactly. I don't know if you can see it properly, but if you take a look at this folder, I don't know how to. I can zoom in. Right. Oh, yes.
So it says constraint as well, sir.
Right. So it's constraint, but you can see here it says constraints.
Oh, there's a S.
Yes. So we have to change. So that's the first change. Now let's go inside this folder. It says constraints underscore top. Here it also says constraints underscore top. So the file name is correct, but there is a mistake in the folder name, or the folder name was not correct. So we have to correct the folder name. Okay. So I think we're done with all the changes that we need to do for the RTL RC underscore script.tcl. Okay, so let's see what the next step. So we're done with step number 6. Okay. Now we have to modify the file that is called constraint file, and we have to make some changes. So let's take a look at that file and let's make the changes. So what is constraint? So just to match with our Verilog code, let's open the Verilog code also. Now we have our Verilog code open. As you can see, the inputs are RST and CLK, clock, and output is Q. The constant file, with the constant file, what we do, we define the inputs and output, and also the delay for each of the gate. And so in order to define the input and output, we have to make sure the name of the input output pins must match. So let's take a look at this. Create clock name CLK. So the name of our clock input is CLK, so that is correct. And we were going to apply a square wave that is called and that is defined by waveform, and it will go to the port clock. Now we have to define the rise time. The rise time is 0.1, and if you go to the clock, the fall time is again 0.1 nanosecond of fall. We'll go to the clock. Okay. And here we have some uncertainty. Uncertainty means sometimes the signal may delay, and sometimes the signal will be slow or fast. So we have to provide some variation with the input, because all the in real circuit the inputs are not ideal, right? So there will be some noise, some other factors also. So we have to provide some uncertainty there. Okay. Now the maximum delay is 1 nanosecond, and it will go to the reset pin RST, and it will also go to the clock pin with maximum. The max for the input and the maximum delay for the output is also 1 nanosecond. But notice that we have the output pin name as count, but in our code the output pin is named as Q. So we have to change this name.
Sir, can we also change things in the code as well, sir?
Yes, you can. So you can name anything, ABCD, XYZ. You can name anything, but those name must match here.
Okay, sir.
So since we have the code, because we write the code first, so we try to follow the pins from the code. Okay. Otherwise, you have to change in a lot of places. Anyway, so but it is your choice. The most important thing is the names must match. So this is the only change that we needed to do, because the output name of the output pin was not correct, so we can change it to Q. So let's take a look at what we have here. As you can see, we modified the name of the output pin from count to Q. So let's go to step number 8. Now write the following command as we have done previously, etc. Synthesis folder. Before that, move to the synthesis folder. All right, so now I think we're ready to run the code, simulate the code and check the output. So let's follow this step. So we have to go out from this folder, then go to synthesis, CSH. Source. CSHRT. If you recall, when we used to run Virtuoso, we had to write Virtuoso. In this case, we are going to run another program called Genus. So we have to write Genus. And Virtuoso does not take any additional parameter, but in order to run Genus, we have to provide some additional parameters. And those are I think we're done. So the command that we need to write is this one: genus space dash legacy underscore UI space dash F space RC underscore script dot PCF. And if we press enter, it will open up a new window. It may take some few minutes to load this program, so just be patient and wait for it to pop up. Okay. So you will see before running the command, before it will pop up a new window, it will start with this command mode. All right. Then we can move to the next step, step number 9. As you can say, a netlist and file and STC file will be generated in the synthesis folder. We will use this during layout design. So let's take a look at it. As we have seen, if you recall, we modify the name of the output files, upcounter underscore netlist.b and upcounter underscore sdc.sdc. So you can see those two files are here. Those are the files that are generated after the simulation. We will see the results a little bit later. In order to see the results from those two files, we have to go to step number 10 and write this command. So GUI, that means graphical user interface underscore show. As you can see, a new window will pop up here, and it should look like this. So the next step, step number 11, let's go to the schematic view and main. You should see this list of the files that we may have. First one will be terms, nets, and standard cells.
In our case, sir, the modules file is absent, sir. Is there any-
No, I think this is, you can see the terms here is 4, but in this case it's 6. So I think this snapshot was taken from different simulation and different circuits. All right. So now we are ready to see the schematic that we have generated. Sometimes it is very slow. Here, if you press the right button, you will see schematic view and then in main. Now you can see, you should be able to see this circuit once you press schematic view in main. So sometimes the software runs very slow, so be patient. So here we have a 4-bit up counter. So as the input we have clock and reset. Here you can see we have some D flip-flop and some logic gates. And at the output we have the signal Q. I think everyone is familiar with 4-bit up counter. I'm not going to go through this, but you should be able to see a circuit like this. Now I have to warn you about one thing. The generation of this schematic is kind of a random process. So some of you may get the same result that I am showing you. Some of you may get different results. So if you get different schematic, it's okay. All right. It's okay to get different schematic. So the schematic may or may not match with this one. Everyone will get different, may get different schematic, or you may get the same schematic. I cannot, nobody can guarantee it before we do the simulation. Okay, so let's go to the
Sir, can we run the simulation as well, sir?
so first we have to generate the schematic. In order to run it, you can run it later. Well, before you do the same schematic, how can you run the simulation, right? You have to generate the circuit first, then you can run. Okay, so that was our main objective for this experiment. Now we can see some other levels that it will generate. So step number 12, you will see the schematic view in your design. Now we know that the power is very important for us. We want to save power as much as possible. So in order to see how much power this circuit will consume, we can go there by using power report and detail report. So let's see what we see in the power report and detail. So in this circuit, we have total 10 cells. The name of the circuit is up counter. We have total 10 cells. The leakage is 10,794 nanowatt. Internally, it's consuming 4,600 nanowatt, and at different nets, because we have some capacitance and resistance from the cable, the connecting wire, that also consuming some power. And if we do switching, the switching power will be something 10,000. So we can calculate this software also provides you how much power it needs to operate this circuit. So in order to see that, we have to use power report detail power. That will give you the description of all the power, like static power, leakage power, switching power, all kinds of power. And this is the conventional power. All right. So this step is done. Now we have to check something that is called DFT. What is a DFT check? The DFT check, like in different parts of the circuit, we can allow certain amount of delay. But if the delay becomes very large, the circuit will not operate anymore. So in order to check if the delay is less than the maximum delay allowed delay, we can verify that using DFT violation. If any signal is delayed by more than the maximum allowed, then that will be a violation of our requirement, because we cannot allow that much delay. If we allow that much delay, then the circuit will not operate properly. Okay, so in order to do that, we have to go to DFT and violations. Here is the DFT violations. As you can see, I don't know you can see it properly, but it says there are no DFT violations. So that means all the signals in our circuit are within our maximum delay requirement. So there will be no, so it satisfies all the requirement. All right. What else? So you can see there is no DFT violation, but because this is a small circuit, so most of the cases we will not see any violation. But if the circuit grows really big and one signal, different parts of the circuit are far away from each other, then we may see some violations, and then we have to fix it. But in this course, we want to keep it minimum, so that's why, and we will not otherwise, unless we do very large circuit, most of the cases we should not see any DFT violation. But there is a possibility that we may see DFT violation, just so that we know. That's what we want. But we are not going to explain or go into detail about it. Okay. So explore the other report generated by CadenceGenus. We have seen the power report. We have seen the DFT report. So you need to go through the detail what it exactly says in terms of power and violations. Now, step number 16. It says that repeat the same process for slow.lib. So let's take a look how we can do that. So let's go back to our synthesis folder. Let's open this one. If you recall, we copied two library files. One of the library file was slow, another one was fast. So the simulation that we did, or the synthesis that we did, we used the library slow.lib. We can do the same process or same steps using fast.lib. Okay. So in order to, and you will see there may be and after doing synthesis with the fast.lib, there may be a different circuit, because slow.lib will have one requirement and fast.lib will have another requirement. The different requirement may provide us two different circuits, but you can do it by yourself. So what you need to do is you need to change it to fast.lib. Okay. And you can repeat from step number 1 to step number 15. Okay. All right. Now, what kind of results that we expect? You should take a snapshot of each of the outputs. What are the snapshots that we need? That I want to see if there is violation for your synthesis. What is the power requirement that you have done, and also the schematic that you will get from your synthesis. So these are the things that you have to provide it in the report. Report text. I don't know what does it mean, but as I mentioned earlier, what you should add into your report all the results, and if you see any discrepancy between the expected output and the result, you can add comment for that one, for that also. I think that's all for experiment number 8. Do you have any question?
Sir, we should add for slow and for fast, two different results.
Yes. So we have done today we have done for slow. You should do the slow also, and then repeat the same process for fast, and add both results for slow and fast in your report. Make sense?
Yes, sir.
Any other questions? All right. If there is no question, that's so we're done for experiment 8 for today. So our next experiment will be experiment 9. So let's see how much time we have. Experiment 9 we will do it on December 4th. and then after that we will have one more week, and we will have lab test during that week. Most likely on 11th, but I will declare the exact date.
Sir, will we have a class on Friday?
Which Friday?
This Friday, because Monday schedule is followed.
I think Monday Wednesday schedule was last Friday. We have already done that.
Because that was Sunday, Tuesday.
Oh no, there will be no lab because Monday Wednesday, right?
Yes, sir.
So our lab is only for Monday. Some other may have classes on Wednesday also. Yeah, that's a good question. I don't know exactly, but let me find it out, and I will post it in the Google Classroom.
Sir, was the server issue fixed?
Yes, that is fixed.
Okay, thank you, sir. Thank you very much.
All right, then. So if there's no other question, I think we discussed all that we need to discuss about today. So I'm not sure about this Friday class, but if there is any, I will announce it in Google Classroom. Otherwise, we will meet on next Monday. Most likely, there will not be any class on Friday because I think we have enough time to cover all the experiments. On December 4th, we will do experiment 9, and December 11th, there will be lab exam.
So are we going to have any sort of lab project, sir?
I have to think about it. I will let you know.
Okay, sir.
Any other question?
No.
All right, so let's do the attendance, then we should be done for today. Okay, can you see my screen?
Yes, sir. Yes, sir.
All right, so something is not right. Okay, so I have to call each and every one. All right. I think there's a, I don't know, Mahmoudul Islam. I think he created this file and looks like there's a duplicate serial number. So pay attention to this serial number because it's not, it's like 1 to 10, then started from 1 again. All right, let's see. 1. MD Mahmoudul Haq Imam. That's it. 2. 3.
Yes, sir.
4.
Yes, sir.
5.
Yes, sir.
6.
Present, sir.
7.
Present, sir.
8. 9.
Present, sir.
10.
Present, sir.
Now 1 again. 1.
Present, sir.
2.
Present, sir.
3.
Present, sir.
4.
So she is also present.
Okay. 5. 6.
Present, sir.
7.
Yes, sir.
8.
Present, sir.
9.
Yes, sir.
10. 11.
Yes, sir.
12.
Present, sir.
Okay, Tamid Aldin, you're present, right? Your mic is not working. Okay. 14.
Present, sir.
15.
Present, sir.
16.
Present, sir.
17.
Present, sir.
18.
Yes, sir.
19.
Present, sir.
20.
Yes, sir.
21.
Present, sir.
22.
Present, sir.
23.
Yes, sir.
24.
Present, sir.
25.
Present, sir.
Okay, 1 again.
Yes, sir.
2. 3.
Present, sir.
4. 1.
Present, sir.
Okay. I think we were done for today.
Sir, Sajid is present, but he
Excuse me,
could not
sir.
say his mic is problem.
Serial number.
10, sir.
Sir, mine too. EC number 3.
Wait.
So my one is triple
Wait.
one.
Okay, who is next?
The
Sir,
triple one.
1. Mahmoud
Yes,
is not
sir.
given 1.
Yes, sir.
Okay, who is next?
Sir, from ECE number